Hey guys, what's up? Eddie Alho here with KissAnalog.com. Today I'm going to use the Omicron Lab, the Bode 100 box down here underneath my computer. And we're going to do some measurements. I got some ceramic capacitors from Vichy on this little card. I got a big one. I think it's a 5 microfarad, big old cap here, ceramic. But I've also got some aluminum electrolytics. And I've got this little polymer aluminum cap. These are supposed to be really nice capacitors. Let's take a look at that. And I've got a Panasonic aluminum. I've also got this inexpensive Chinese one I took off one of my audio boards I got. Put some, I think I really need higher voltage, but I thought, plus I'll put better caps. But let's see how good this little guy actually is, that little aluminum electrolytic. And then I've got some inductors, kind of a big one here, and a smaller one. Measure a couple inductors as well. I also want to measure these resistors. They're supposed to be non-inductive. I use them for audio testing, and yeah, this is a 200 watt. There's a 4 ohm. I've got 8 ohm. I've got a couple of each actually, so when I'm doing 2 channels. And then I've got one of these big guys, and I was kind of hoping I had 2 of these. But anyway, this is a 4 ohm. Well, roughly 4 ohm. And the way it's made is a piece of ceramic, basically, and they take a piece of wire, wrap it around, and then they wrap it back the other way so the fields cancel. So let's see how well that worked and how non-inductive that really is. But I want to show you the curves. Instead of using my meter here, I have this Handtech. I've got a bunch of these other little small meters, these little LCR meters, but now these meters, especially this Handtech, I think there's 5 different frequencies I can test to, and there's some things I want to point out about this, but I think I'm going to do another video where I compare the Handtech and maybe some of those other lower cost LCR meters to what we see on the Omicron results, okay? Because the advantage of the Omicron is you get a full curve across whatever frequency band that you can do on this thing, instead of just these discrete frequencies, which something like the Handtech is actually a pretty good tool. You can actually build a curve because it has so many frequencies, from all the way from, I think it goes down to 100 hertz to 100 kilohertz. So you can pretty much build a curve between that. We'll go out to about 10 megahertz on that, so we can see actually what's happening to these parts. Now, these parts, they have what we call parasitics, and that's the kind of thing that rides along with the part that you don't really want. For instance, like I said, non-inductive resistors. You don't want inductance in your resistors, but you get some. It just comes along for the ride. So they're called parasitics. With capacitors, you'll get some inductance. Maybe not much, but you get some. So if you go out to a high frequency and you're expecting some EMI filtering or such, then you're going to find out how good they're going to work. Even down to 100 kilohertz, you might be surprised at what this does or doesn't do. So, yeah, it's really nice to see. Now, one of the other things you get with, inductors, you get a little capacitance, right? You get capacitance from winding to winding. So inductors, you get capacitance. Capacitors, you get inductance. But also with both of these parts, you get some resistance, right? Because this guy's made with wire, so you're sure you're going to get resistance. DC resistance, DCR. And we know with capacitors, we get ESR, equivalent series resistance. So, yeah, we'll see how that works out with this aluminum polymer, this high-grade capacitor, and these other guys, and even the little cheap Chinese one. Okay, let's come over here, take some measurements. All right, guys, we're here in the Bode Analyzer Suite, and I'm going to go to New, make sure I'm in the right place. Yes, I am. There's Vector Network, Impedance. I'm right here. So we're going to select this one because we're going to just go to 2 leaded devices. So that should be great. So let's select that. We're going to discard the last measurements. All right, now let me show you the setup. Okay, it's 10 dB attenuation on both receiver 1 and receiver 2. Both receivers have the switch tied to these lines, which go across this 50 ohm resistor that is going to the output. So there we go. So one's on the input of the 50 ohm, one's on the output, and we should be able to detect whatever's connected out here. Okay, now also let's go to the calibration thing. You know, I've already done one recently. Oh, it says not performed. Oh, because I'm starting a new measurement. Okay, I opened my connection. By the way, I'm calibrating right at the terminal because the leads aren't going to make that big a difference. You know what? I'm gonna do it at the end of the leads just to do it that way. Okay, now I'm going to short the two ends together, two alligator clips. So this one will take into account any of the lead impedances. Okay, now we're going to go to the load, and I got a 50 ohm load, so I'm going to connect that guy up, and let's run that one. All right, we should be good to go. Oh, and just to make sure, I have the 50 ohm load down here, so that's what I calibrated with, so that's good. Okay, while I still have the 50 ohm load connected, let's just run a plot and verify. So the red's on the top. See over here on the top right border, trace 1 is red, trace 2 is the blue, and there we are. If you see 10 ohms right here, 20, 30, 40, 50. So, and it's real flat, except for right out here past 10 meg, the phase kind of drops down just slightly. So, you know what I can do? We can really zoom in on this. I'll auto optimize. Now look at that. Now this is 51 ohms, and it comes down here about 1 meg, and it keeps on auto optimizing. But it goes from 51 to 49 ohms. So that's pretty close, guys, right? That's zoomed in real tight. It's kind of annoying watching that, huh? You know what else I'm going to do? I'm going to go to 100 hertz. That'll slow it down a little bit, and it'll give it a little better resolution. All right, so here, let me see if I can, I think if I say, is it optimize? Yeah, okay, there we go. So it's just below 52.5. Up here you can kind of see. Here, I'll type in 10 hertz up here on top. So it'd be right on the left border. And see, it starts off at, well, sorry, went to 100 hertz. Oh, I'm scanning from 100. Can I do 10? I thought I set this up. Okay, and I'll do 10 to, I guess I forgot to, 10 to 10 meg. Well, that really slowed it down with the 100 hertz thing. But here's 100 hertz, and I will do the other one at, wow, that's interesting. So look how flat the magnitude, and look, it's coming out right across 50 ohms right across here. This is looking good, right? Now, it does kind of do this phase thing, which this is 0 and this is only like -1 degree. So that's ridiculously, here I'll okay, it's already on optimize, so I'll just leave it there. And yeah, so this is looking pretty flat, I think. I hope you agree. Okay, I'll disconnect that. I'm going to start off with the big old aluminum electrolytic just for fun. Want to make sure it's shorted out before I connect the leads to it. And let's see what, I'm going to have to auto optimize over here. There we go. Alright guys, this is a Cornell Doubler capacitor CDE, and it is the SLPX series 6800 microfarad 63 volt. So look at the red. It looks like a capacitor from 10 hertz down to about 1K, right? And then right about 1K it flattens off and it starts looking kind of resistive between 1K and 100K. And then it goes up in impedance because it's becoming inductive at that point. So, and you can see the phase starts off at minus 90, which a capacitor should be, right? But then as we see this zero where the ESR makes a zero in the impedance, so then what happens is as this goes from 20 dB per decade down to flat, we change phase, and you can kind of see how that's happening. But then as it goes flat and it goes back to plus 90 degrees, you see the phase drop back down. So yeah, it's just following the different poles, or zero and pole here on the well, it's actually like two zeros, right? Because it starts off zero, flattens off, and then goes zero again, it goes up 20 dB. So all right, so there we go. There's the big old aluminum electrolytic. Pretty interesting. It lets you know that from about 0 to 1 kilohertz, it looks like a capacitor. After that, not so much. Okay, now let's go to another aluminum electrolytic. This one is 1000 microfarad 50 volt. And this is one of those, lower cost Chinese caps, okay? Actually, this is a Panasonic, so, sorry, this isn't a Panasonic. At least it's labeled as a Panasonic. Okay, here we go. Again, 1000 microfarad 50 volt cap. Now, this will tell us how good of a capacitor it is and for what frequencies. Now, look, pretty much the same kind of plot. Although this one goes out to about 10 kilohertz before it becomes resistive and flattens out. And where these flatten off, by the way, is more or less the ESR of the capacitor. Now, when it's not really sharp at the bottom, it probably is the ESR. And it stays down the ESR, which is down around 20 milliohms, which sounds about right. And then it goes back up inductive. So, and look, it's kind of, it has some kind of weirdness down there at the bottom, right? Okay, I just kind of moved the leads around. So, okay, I'm putting the leads back next to each other. Yeah, so these leads, if you let them spread apart, it changes the impedance just a little bit. It lets some more of that inductance come into play, I think. When you hold them together, I think it cancels that. Now, I do have that impedance block I could use. Some of these devices I can't use it, but these particular ones I could actually. So, here, maybe I'll try that in a minute. Okay, here let's go to another aluminum cap. Now this one here is actually a polymer. It's an aluminum polymer cap, so this will be interesting to see. This one is a 270 microfarad 25 volt. All right, well, look at that. It looks capacitive all the way down to about 10 kilohertz. And then it kind of flattens off in the ESI range, and then the inductance takes over and it takes back off. So, but all the way down to about 10 kilohertz, it's looking like a nice capacitor. And the ESR does drop fairly low. But if you're operating this in a switching power supply at a couple hundred kilohertz, you're not going to get a lot of you're going to have some ESL in there. So that's why you always need ceramic capacitors in parallel to these aluminum caps. All right, so here, let's do a poly. This is a polypropylene capacitor. Okay, this is a 15 microfarad, 100 volt BC capacitor. So it's nice quality MKT. So it's polypropylene. And yeah, this is a nice quality capacitor. You can see it starts off with a low impedance on the left side of the graph. And look how far, man, it goes all the way out to 100 kilohertz before it hits its resonance and comes back up. So this is a great capacitor for switching power supply, right? Now you'd still want, you know, if you're down operating around 100 kilohertz, this is ideal almost for that, because it's just all ESR at that point. 100 to 200 kilohertz it looks like. And it's pretty flat down there. And where it's really becoming resistive, it's interesting how the phase kind of acts up. It's actually interesting how the phase is pretty much flat, minus 90, all the way out there. And then all of a sudden it takes this, you know, big old spiky thing up. Now if I lowered the resolution here, let's see if I do that, if we can clean that up. Let's go to 30 hertz. That's better resolution on the bandwidth of the receiver, so it's got a tighter filter. But wow, it still follows those spikes. Now what we could do, we could experiment and try to turn up the source level a little bit and see if that has any effect. Okay, go up to 10 dB, see if that affects it. It did change it a little bit, right? So sometimes when you see these kind of strange spiky things occurring, if you either improve your resolution, bandwidth resolution, or increase your source level. Now I think that's about as high as I can go, plus 13 dB. But that did kind of improve the picture, right? So you could probably smooth out those spikes and kind of smooth out that hump for the phase, because if you look at the gain, there's a little bit of a notch down the bottom, but otherwise it's pretty smooth. So the phase is probably something that's an artifact or something. Now if I go to this impedance thing here, let's see if I drop my attenuation. I might have too much signal now. Yeah, I have too much signal. I still have too much. Okay, so it didn't, I got a little bit more gain than I had. It keeps on auto adjusting the graph, so you have to look at the left and right borders to see where we are. But yeah, it looks like it's not changing a whole lot. But yeah, that's kind of an interesting exercise there, just to show you how you can try to fine tune things. Alright, let's go to I thought I had another small poly, but you know what, let's go to this little ceramic capacitor. And you want to see, a ceramic capacitor, right? Here you go. This is a 10 microfarad ceramic. I think it's a 50 volt 10 microfarad. Very flat at minus 90 degrees. And kind of a little bit of a bump, but that's not bad. Wow, holy cow, that phase, I can't believe how... Okay, there it goes. But still, it's going from minus 90 to minus 76. It looks, that's the other thing, is you have to look, if I set my boundaries so it wasn't jumping around, it's magnifying everything to get the full, size of the screen to really zoom in on it. So really, minus 75 is at the top, minus 89 is at the bottom. So that phase is pretty darn flat. But you can see this is good out to, you know, past 100K before it becomes resistive. About 200K there, it hits a resonant, and it's dampened because it's a nice smooth bottom, just like all these capacitors have been. But, you know, for a ceramic, I'm kind of impressed with how, with the bottom of that curve, I almost expected it to be a little bit sharper. But then again, you know, we're going from 1K all the way down to, what is that, 100 milliohms at the bottom of the screen. So the ESR is hitting right down about 100 milliohms at 200K. So that might surprise you too, right? So, okay, let's go. Now that's a 10 microfarad, kind of a lower cost type of ceramic. I'm going to go to this capacitor that I took off of a amplifier board. It's called a Sam Young manufacturer, and it's a 470 microfarad 25 volt. Let's just see what kind of quality this thing might be. I suspect that, you know, I don't know. I replaced them because it was a good amplifier that I was doing, and I wanted to get some well-known good capacitors on it. And also I think I needed a higher voltage rating. Okay. Actually, these are looking pretty good. Wow. Alright, guys, look at that. This was just a no-name capacitor taken off a cheap Chinese amplifier, and it looks pretty good all the way up to 10 kilohertz. So, and it's dropping down to, God, what is that, 20 milliohms or something down the bottom of the screen. So almost just above 10 milliohms. Geez, guys, that's actually fairly impressive. It's a good thing I kept them. There's a bunch of them that I took off, so I kept them. Anyway, all right. Hey, inductor time. This is going to be a small inductor here, okay? Let's see what it does. I probably should have done the curve first and had you guess what kind of part it is. Okay, you can see it starts off really low impedance, down around 20 milliohms, and then the inductance kicks in and it takes off. And you can see the phase started off down near around 0, you know, around 5 degrees, and then shot up to plus 90 as it became inductive. And then off to the right, you kind of see it starting to bend. You know, it's the 20 dB slope is kind of bending right about the time it hits the phase. And you can also see from the phase that to look for that, because you can see the phase is going from 90 back down to 0. So it's going back to, you know, at the end of that, it's starting to look, I'm not sure what's going on. It's almost looking resistive. You know, it's so at the end of that, I think the capacitance between the windings is starting to affect it. So you're starting to see you're going to see the resonance of the inductor if we went out a little bit further. But that, you know, that resonance is actually out there pretty high frequency. So for switching power supply, except for the EMI filter, you probably wouldn't care about that. In the EMI filter, you would care about that maybe. All right, so now this coil has a lot of turns on it. Okay, it's gonna be a little higher inductance, but it's a lot of turns, and so we should see maybe the capacitance in the windings kicking in. Wow, look at that. Sure do. And look at that resonant peak. So isn't that interesting? That's a good story to tell. You start off down around 100 milliohms, and then it goes immediately inductive because there's... Now from that slope, we could calculate the inductance. Any one of these, like let's say at 100 ohms there, it crosses 10 kilohertz. So you could calculate the inductance right there. So 10 kilohertz is equal to 2 pi FL, and F is 10K, and the impedance is 100 ohms, so you can change the equation around and calculate L. and it crossed right through that crosshairs, so that'd be a good one. But that's interesting. Out about what, 2, 3, 4, 4.5, kilohertz, something like that. Let's see if I can drag the right over here, right there. You can see that that's about 436 kilohertz, it says, and it really took a resonance there. And so if this was a filter that you cared about to filter something in that frequency range, you'd want to put a resistance in series with it. The good way to do it is put a little resistance in series, and it would dampen that spike right there. Okay, so yeah, there you go. But an inductor like this you're going to use for, a buck boost. You could use it for a filter too. And if you're filtering 60 hertz, 120 hertz type stuff, then you're a long ways away from 400 kilohertz. All right, so that was kind of fun. That's just looking at a bunch of components with your... Oh, you know what? Here, let me get a good quality ceramic. Let's look at that. This is a 5 microfarad ceramic capacitor. It's a 3640. It's a big cap. This should look great. Okay, it's starting off around 3K at 10 ohms. And look at it drop down 20 dBs per decade. Wow, look at that. It's going to go out to megahertz. That's pretty awesome. So this cap would be an awesome cap to put at the output or input of a switching power supply. This is a fantastic capacitor. And not only that, it's, let's see, was it 90? It's down around, what is that ohmage? You see 100 milliohms, it's 90, 80, 70, 60, around 50 milliohms maybe. Oh, went down a little bit lower. So yeah, it's down there at about 1 megahertz. And you can see the phase is minus 90, and then as it starts to slope up, the phase goes up just like we'd expect. Alright guys, so when you're doing analysis like Bode plots and that, it's nice to know how much your test equipment's affecting your results, right? So it's really nice to have, sophisticated stuff, and you can do this stuff. I've shown how to do this with the GWN stack. So you may not get the precision, but you get good results. So, and you can do it with the picoscopes. So there's other, if you can do a Bode plot, you can do impedance measurements. And I'll put the link down below where I show how to use the GWN stack to do that, okay? But yeah, knowing what your capacitors are actually doing in your circuit, if you're hand winding inductors, like this guy was handmade, if you're hand winding 1.5 millihenries, in case you're wondering, if you haven't done the math yet, let me know what the math turns out to be. It's supposed to be 1.5 millihenries, but yeah, when you do inductors for power supplies like we're going to do in these power supplies that we're designing, we're going to want to wind them, and we're going to want to know what that resonance is, where it is at the frequency. We certainly don't want it happening anywhere near our switching frequencies, so it really is nice to be able to graph them. So whether you do it on an Omicron or you have another way to do it, it's just showing the importance of actually knowing the curves of your passive devices. They seem simple, but there's actually some stuff going on. Alright, let's get back to measuring. I want to show you the resistors now, okay? They're supposed to be non-inductive. I hope they are. Alright guys, so for my speaker, I'm just going to do the, I'm going to just go from 10 hertz to 1 meg, okay? Now, that looks like about 8 ohms. This is the 8 ohm load. And then, wow, it starts looking like the phase is shifting, and this is 10 degrees, so yeah, it's 45 degrees up here, you know, so we're getting out to 20K. We're getting about almost 20 degrees phase shift here. If I go 20K here, so it's about 8.6 ohms and about 16 degrees. So right here, I think I'll go 10K just to show you the difference. You know, let's go 1K on this one. So we can see at 1K it's 8.2 ohms, and 20K it's gone up another 0.2 ohms, so not too bad. But you can see here at 1K it's it's pretty much 0 degrees. So we have about 16 degrees phase shift at 20K. So not bad, but not flat. Okay, let's go to the 4 ohm metal one. Okay, here's a 4 ohm. Curved up at, yeah, it looked like it might have stayed a little flatter, a little longer maybe, I don't know, let's see. Okay, it looks like about 4 ohms all the way out. Okay, so 1K we see 4.17, and 20K 4.7 rounded off, and it's changed 22 degrees. So at 1K it's changed 1 degree. So actually that's probably changed a little bit more than the 8 ohm. The 8 ohm has more resistance per inductance. That's probably why. Okay, let's see. Here's our 4 ohm 300 watt, the green one. Looks flat. Wow, it did better. Look at that. At 1K and 20K, it's almost the same ohms, and it only changed maybe a couple degrees at 20K. So yeah, the green one looks less inductive. That's pretty awesome. All right, guys, so I might have to give me some more of these resistors. I mean, this resistor actually did better than these fancy dudes. I like these because they were kind of small, 200 watts. This one here is, I think it's rated, yeah, 300 watts. So, you know, 4 ohm, 200, 4 ohm, 300. Plus, it's not, you know, we saw it wasn't right at 4 ohms, right? It says 4RJ, but yeah, it's not quite right on 4 ohms. But I like the fact that it goes out to a higher frequency before the inductance kicks in. So, I think I'm going to get more of these guys. It's a good thing I looked at it with this, right? You know what? I'm going to do another video compared to the Handtech, alright? And I've got another LCR meter that I'm going to show you. I just got it. Pretty excited about it. So, got me thinking about this. Omicron's awesome because it can do all this stuff. So, alright guys, thanks for watching. And, oh, by the way, 2 thumbs up to my patrons. Really appreciate you guys. You can become a patron. Links down below. Or if you just want to, you know, one-time thing, like there's a thank you button down below. That's kind of cool. But the thumbs up button, I really appreciate that one. It's a free way to help the channel. And it really does help the video. YouTube Analytics, they share it more if they think people like it. So if you liked it, I appreciate you hitting that thumbs up down there. So thanks for watching, guys, and we'll see you next time.